For decades, the concept of teleportation has captivated the human imagination, immortalized in science fiction as the ultimate form of instant travel. From the iconic Star Trek transporters to the fantastical worlds of comic books, the idea of moving matter or information across vast distances in the blink of an eye has been a tantalizing dream. But what if this dream wasn't just the stuff of fiction? What if it could become a reality? Thanks to a groundbreaking achievement by scientists at the University of Oxford, quantum teleportation, a concept once relegated to the realm of theoretical physics, has finally been realized. This astonishing breakthrough could reshape the very fabric of how we perceive space, time, and the limits of human technology. But what exactly is quantum teleportation? How did these scientists achieve it? And what could this mean for the future of technology, communication, and even human existence? Let's dive into the details of this monumental discovery and explore how it could alter the course of scientific progress in ways we can barely begin to imagine. Quantum computing has taken a giant leap forward as researchers at the University of Oxford have successfully demonstrated quantum teleportation of logical gates, a milestone that could redefine the future of computing. The breakthrough solves a major challenge in the field: scalability. With this innovation, quantum computers could soon transition from experimental research to industry-disrupting technology. For decades, quantum computing has remained a theoretical marvel, offering the promise of machines that could outperform even today's most powerful supercomputers. Unlike traditional computers that process information in binary, ones and zeros, quantum computers leverage quantum bits, qubits, which exist in multiple states simultaneously due to a property called superposition. This allows quantum systems to solve complex problems exponentially faster than classical computers. The challenge, however, has been scalability. While individual quantum processors have been developed, linking multiple processors together in a way that maintains quantum coherence has proven to be extremely difficult. When we think of teleportation, our minds often drift to the flashy depictions seen in movies and TV shows. Think of Star Trek's transporters, where a crew member steps onto a platform, is dematerialized into a stream of particles, and then reassembled in another location. While this makes for great entertainment, the reality of quantum teleportation is quite different, and in many ways, even more fascinating. Quantum teleportation has been demonstrated before, but this is the first time it has been used to transfer logical quantum gates, the building blocks of quantum algorithms, between separate quantum processors. This is the equivalent of connecting multiple traditional computers into a network, except in this case, the data moves without physically transferring qubits. Quantum teleportation doesn't involve the physical movement of matter. Instead, it's about the transfer of quantum information from one particle to another, instantaneously and without traversing the space in between. This process relies on the strange and mysterious principles of quantum mechanics, particularly two of its most mind-bending phenomena: quantum entanglement and superposition. The researchers achieved this by carefully designing interactions between quantum systems, allowing them to execute quantum logic operations across a network. This means separate quantum processors can be wired together into a single, fully connected system, something previously considered an enormous challenge. This breakthrough enables us to effectively wire together distinct quantum processors into a single, fully connected quantum computer, said Dougal Main, lead researcher from Oxford's Department of Physics. The future of a quantum internet beyond just computing, this teleportation technique could serve as the foundation for an ultra-secure quantum internet. Unlike traditional communication networks, a quantum internet would rely on the principles of quantum entanglement, making it virtually immune to hacking. Governments, businesses, and researchers around the world are actively pursuing such technology to revolutionize secure communications, sensing, and distributed computing. A major milestone in quantum computing has been achieved after researchers at the University of Oxford built a scalable quantum supercomputer capable of quantum teleportation. The breakthrough centers on the so-called scalability problem of quantum computing, with the researchers claiming it will allow the next-generation technology to be realized on an industry-disrupting level. The field of quantum computing has been around for decades, but only in recent years have significant advances been made towards realizing them on a practical scale. Utilizing the properties of quantum physics, these next-generation machines replace traditional bits, the ones and zeros used to store and transfer digital information, with quantum bits, qubits, which can act as a 1 and a 0 at the same time through a phenomenon known as superposition. This gives quantum computers the potential to be orders of magnitude more powerful than today's state-of-the-art supercomputers that use conventional computing technology. At the heart of quantum teleportation lies the phenomenon of quantum entanglement, often described as the most mysterious aspect of physics. When two particles, such as photons or electrons, become entangled, they form a deep connection that links their properties, no matter how far apart they are. This means that a change in the state of one particle will instantaneously affect the state of the other, even if they are separated by thousands of kilometers. Albert Einstein famously referred to this phenomenon as spooky action at a distance, as it seems to defy the speed of light, a fundamental limit in classical physics. Yet, experiments have repeatedly confirmed that entanglement is real, and it's this eerie connection that makes quantum teleportation possible. What is quantum teleportation? Quantum teleportation is the process of transferring the quantum state of one particle to another distant particle without physically moving the particle itself. Here's how it works. 1. Creating entangled particles. Scientists first create a pair of entangled particles. One particle stays with the sender, while the other is sent to the receiver. 2. Encoding information. The sender interacts with their particle, altering its quantum state. Because the particles are entangled, this change is instantly reflected in the receiver's particle. 3. Transferring the state. The quantum state of the sender's particle is effectively teleported to the receiver's particle, without the particle itself traveling through space. It's important to note that this process doesn't involve the physical movement of matter. Instead, it's the information about the particle's quantum state that is transferred. This might sound less dramatic than the teleportation of objects or people, but its implications are nothing short of revolutionary. Teleportation is a quirk of physics that only makes sense through a quantum lens, where objects exist in a blur of possible characteristics until processes of measurement force them to adopt each state. By mingling the undecided states of different objects in an act known as entanglement, and then carefully choosing the right kinds of measurements to make on one, it's possible to use the answers to force an entangled object some distance away to adopt and destroy the original object's quantum identity. It might not be the kind of teleportation that would beam passengers through the vacuum of space in a blink, but it's perfect for sharing the blur of information necessary for logical operations in a quantum processor. Previous demonstrations of quantum teleportation have focused on transferring quantum states between physically separated systems, says lead author Dougal Main, a physicist at Oxford University. In our study, we use quantum teleportation to create interactions between these distant systems. Where classical computers use binary on or off switches to perform strings of computations on bits of information, quantum computers use mathematically complex distributions of possibilities known as qubits, typically represented in a simple feature of an uncharged particle, such as a charged atom. To make this process practical, hundreds or even thousands of such particles need to have their yet-to-be-decided states entangled with one another in a restricted fashion, without intrusive objects weaving their own possibilities in and messing up the calculations. Scaling current technology to this level is complicated by obstacles that require error-correcting processes or shielding to preserve the delicate quantum states long enough for them to be measured. The Oxford Breakthrough. How it happened. For years, scientists have been working to achieve quantum teleportation, but numerous challenges stood in the way. Quantum states are incredibly fragile, easily disrupted by external forces. a problem known as quantum decoherence. Maintaining entanglement over long distances has also been a significant hurdle. The Oxford team overcame these challenges through a combination of cutting-edge quantum technologies and a deep understanding of quantum mechanics. Their breakthrough involved the use of entangled photon pairs, which were created in the lab and then separated across a distance. The key to their success was ensuring that the entanglement remained stable long enough to transfer information. Using advanced techniques to shield the photons from interference, the researchers were able to encode quantum information onto one photon and successfully teleport it to its entangled partner several kilometers away. This achievement marks the first time that quantum teleportation has been demonstrated over such a distance in a controlled laboratory setting. Why this breakthrough matters. The successful teleportation of quantum information is a monumental step forward for science and technology. Here's why this breakthrough is such a big deal. 1. Quantum computing. Quantum computers rely on qubits, which can exist in multiple states simultaneously, thanks to superposition. Quantum teleportation could enable instantaneous communication between quantum computers, paving the way for ultra-fast quantum networks. 2. Secure communication. Traditional encryption methods are vulnerable to hacking, but quantum encryption could provide unbreakable security. Quantum teleportation could be the key to building these secure networks. 3. Space exploration. Quantum communication could revolutionize how we communicate with spacecraft, enabling real-time data transfer across vast distances in space. The future of quantum communication. One of the most exciting implications of quantum teleportation is its potential to revolutionize communication. Unlike classical systems which rely on electromagnetic waves, quantum communication uses the principles of entanglement and superposition to transmit information. This could lead to the creation of a global quantum internet, a secure, lightning-fast network that could transform industries ranging from banking to healthcare. Quantum communication also offers inherent security. Any attempt to intercept the information would disturb the quantum state, making the intrusion immediately detectable. This could pave the way for unbreakable encryption and a new era of secure communication. Challenges ahead. While the Oxford breakthrough is a significant milestone, there are still challenges to overcome. Scaling up quantum teleportation for real-world applications will require advancements in quantum technologies and infrastructure. Maintaining quantum coherence over long distances and developing quantum repeaters are among the key hurdles that scientists must tackle. A new chapter in science and technology. The achievement of quantum teleportation by Oxford scientists represents a revolutionary leap forward in our understanding of the universe. For centuries, we've been constrained by the limits of classical physics, the speed of light, the boundaries of space, and the challenges of communication. But with this breakthrough, we've taken a giant step toward a future where these constraints no longer apply. As we continue to explore the potential of quantum mechanics, we may soon find ourselves in a world where quantum teleportation is not just a scientific curiosity, but a cornerstone of technology, communication, and exploration. The quantum revolution is here, and it's only just beginning.